For number 9, we're given a bunch of information about the data set. And if you look in your textbook on page 210, you can use that information given to find the slope and the y-intercept, and then you can figure out the least squares regression line. So plug in those values that are given and calculate that. But then check your work, and when you can use StatCrunch to do that. So regression, simple linear, x and y, and then hit compute. And so you see what your slope should be and your y-intercept should be, and then plug those in. And also looking in StatCrunch using the button over, you can get the idea of what the regression line should look like, and then you match that up to the correct graph. The key is that your y-intercept needs to be at 6.44, and so you can use that to quickly throw out the graphs that have the wrong y-intercept and choose the correct one. And number 10, open the data in StatCrunch. And we're going to do simple linear regression on x and y, and find the slope and y-intercept and plug those in for your least squares regression line. And then once again, look at the picture in StatCrunch to help you determine what the graph should look like, the scatter diagram, but also just make sure that you have a y-intercept at negative 1.7, which would be down here kind of off the chart. So these are definitely wrong because they have a positive y-intercept. And then this one has a negative y-intercept, but all the data is in a perfectly straight line, which isn't the case. So this is the only possible option, and it does match what we have here in StatCrunch. For 11, open it in StatCrunch. And regression, simple linear. You get your slope and your y-intercept. So plug those in, y equals mx plus b, slope, and then y-intercept. And then the sum of the squared residuals. And that's also told to you in StatCrunch. Remember, residuals are errors. So look down at this table where it says error, and sum of the square for our error would be 13.5. And what the residuals are measuring is how far away the data points are from the line. And the reason we have to square them before we sum them, so if you took away how far this data point is from the line, it's below the line, so it's negative. And this one's above the line, so it has a positive difference. But if you added together negatives and positives, they'd cancel each other out. So if we square everything first, when you square a negative, it becomes positive. So we measure the error, how far away every point is from the line, square those values, and then add them all up. And that can take a bit of work to do by hand, so it's nice that StatCrunch, Excel, programs like this that can do that for us almost instantaneously, and we can just look it up. So the sum of the squared residuals is 13.5. For number 12, we have an equation, a least squares regression equation already given to us. And when trying to predict, the y value stands for winning percentage based on a team's on-base percentage, and x is the on-base percentage. So I'm going to scroll to the top here. The slope is positive, which means they're going to move in the same direction. So as on-base percentage increases, winning percentage will also increase, and the slope tells you by how much. And so for each percentage point increase in on-base percentage, the winning percentage will increase by the slope percentage points, and that's on average. That's our prediction. For this baseball season, the lowest on-base percentage was 0.310 and the highest on-base percentage was 0.366. Does it make sense to interpret the y-intercept? And so we only want to use this equation to interpret values in between these two. Nothing lower than that, nothing higher than that. A y-intercept is when the x value is 0. So it would correspond to an on-base percentage of 0. And that's definitely outside our range, so it doesn't make sense to interpret the y-intercept. And also think about it, the y is standing for winning percentage. a winning percentage can't be negative, so it really just doesn't make sense in this case to interpret the y-intercept. Would it be a good idea to use this model to predict the winning percentage of a team whose on-base percentage was 0.220? No, it's not a good idea because 0.220 is outside of that range. A certain team has 0.322 on-base percentage and a winning percentage of 0.546. What's the residual for that team? And then let's interpret it. So 0.322 is definitely in between our range, so we can use this model to predict their winning percentage. And so you can use a calculator, but you're basically just going to be plugging 0.322 in here for x. So I did it in Excel. Our prediction, if some team has an on-base percentage of 0.322, plug it in. Your prediction is this will be their winning percentage. The problem tells us this was their actual winning percentage. And so the residual is just the actual minus the predicted. So we get a positive number because they actually did better than predicted. Their actual percentage was better than the prediction we got. So plug that back in. The residual was there, and then interpret it. The residual indicates that the winning percentage of the team is above average. They did better than the prediction. So they're above average for teams with an on-base percentage of 0.322. For number 13, we're trying to use a child's height to predict their head circumference. So we got our data. We can open StatCrunch. And we're trying to use a child's height to predict their head circumference. And you get the slope and the y-intercept you need to predict to make the least squares regression line. So y equals mx plus b, put the slope and the y-intercept in there. And then interpret it. The slope is positive, which means they'll move in the same direction. So as height increases, head circumference will also increase. And this tells you by how much. So fill that in. Interpret the y-intercept. Well, the y-intercept would be, again, when x is 0. So when someone's height is 0, what is their head circumference going to be? And we don't want to use this model to predict that. First of all, just kind of logically, a height of 0 doesn't make sense. So it's not going to make sense to use this model. But look at the data for heights. We only want to use our model for values that are within the range of our data. And it looks like our smallest is about 24.5 and our largest is 27.75. So anything between 24 to 28 we could use the model for, but once we get outside of that range, the model's not going to be a very good predictor of head circumference. So it's not appropriate to interpret the y-intercept because a height of 0 is outside the scope of the model. The next part wants us to use the equation to predict the head circumference for a child who's 25 inches tall. Just plug a 25 into our equation and we'll get our prediction. So that's our predicted head circumference for someone who's 25 inches tall. And then let's look at our child who actually was 25 inches tall in our study. So 25 inches tall, their head circumference was 16.9. So we take their actual 16.9 and minus our residual, and minus our predicted result, what we expect on average, and that gives us the residual. So negative 0.13. So they're below average, they have a negative residual. And then let's draw the least squares regression scatter diagram. You can use StatCrunch to get your idea of what it should look like. The residual would be a picture of how far away that child who is 25 inches tall is from the line. So the residual is always the distance from our actual points to our line we draw. And so it's drawn here at the little dash. This is the correct scatter diagram with the residual drawn in that distance between the real person who was 25 and then our prediction for the person who was 25, which is where the line is. And that child is below average because their plot on the scatter diagram is below the line, which that line is our average prediction. In this part, says that there were 2 children who were 26.75. They're both right here together, and they have different head circumferences. Nothing's wrong with that. The line's giving us an average of what we predict somebody to have, but it doesn't mean everyone's going to have exactly the same head circumference for if they're the same height. So for children of any given height, head circumference will vary. And would it be reasonable to use our least square regression line to predict the head circumference of a child 32 inches tall? The answer is no. Again, our data really only works for about 24 to 28 inches tall. That's where our data ranges from. So we definitely don't want to go outside that range to make predictions. So 32 is definitely outside that range. Number 14, we're trying to see if there's a correlation between the number of colas consumed in a week and the bone density. So open it in StatCrunch. We're going to see if number of colas in a week affects bone mineral density. And to find the equation, we have our slope and our y-intercept. Round as appropriate. And get your equation of your least square regression line. And the slope is negative, so it means they're going to move in opposite directions. As colas go up, bone density is going to go down, and this tells you by how much. So for each additional cola consumed, as colas go up, bone mineral density will go down. It will decrease by that much. Can we interpret the intercept here? Yes, we can. The intercept would mean no colas per week. And no colas per week, that fits into our data. We have information on people from no colas all the way up to about 8 colas. So anything in that range, 0 to 8, anywhere in between, it'd be okay to use our least square regression line. Anything between 0 and 8 colas per week. And so we can interpret somebody who has 0 colas per week. That's what the y-intercept is. So it's saying that that is their predicted bone mineral density. And then let's predict it for someone with 4 colas per week. So we can just use a calculator. You can use Excel or a handheld calculator, or I just have one on my computer here. Alright, so negative 0.003 times 4 colas per week, and then add 0.8865. And you get, that's your predicted bone mineral density, 0.8745. And MathLab will accept values close to that. It has 0.8746 here, so it because we rounded up here when we produce the slope and the y-intercept, some answers will be rounded a little bit differently. So it accepts anything close to the 0.8745, 0.8746 range. So it's good like that. It won't count you wrong if you're just off by decimal at the end. Alright, so researchers found a woman who consumed 4 colas per week to actually have the density of 0.873. This is below average. Here's the average that we predicted, and this person was below average. And would you recommend using this model to predict bone mineral density for a woman who consumed 2 cans of cola per day? So look at our data again. Not 2 for the whole week, but 2 per day, which would put that woman at 14 colas per week. That's definitely outside the scope of our data. We're only between 0 and 8. So for someone who is drinking 14 per week, no, we don't want to use this model to predict their bone mineral density.